Okay, we define the derived set and a limit point. So we'll look at an example. So the question is, find the derived set of A. We'll take the same example that we took for the interior points. So we'll take the interval, open interval 1, 2. Okay. Now, if I take any inside point and I take any open interval, we will have an intersection with A other than at X. So any point inside is going to be a limit point, and that's clear. And the next thing is we want to check the endpoints. So now I take 1 and check whether 1 is a limit point. So if I take any open interval, and you can see that this open interval will intersect part of A. How small I take this interval, always there's going to be an intersection with A. So that means 1 is a limit point. And similarly, 2 is also a limit point from the right hand side. So that means the derived set of A is going to be the interval 1, 2, the closed interval 1, 2. And if you remember, the interior of A was the open interval 1, 2. The endpoints weren't included. So now we have a good understanding about the interior and the derived set, so that we want to get a connection between all these definitions. The next definition is the closure. Okay, so the closure A bar of A is the set. So we take A bar to be A union the derived set. That means you take the union of A together with all its limit points, and we call that the closure. Okay, we look at another example. Okay, we'll take A to be left closed, right open interval 0, 1, and we are going to take the standard topology, R with the standard topology, and this is similar to the last example. So this is my A, and we can see that 0 is not in the interior of A. The same argument follows from the last example. So this will tell me that the interior of A is going to be the open interval 0, 1. And if I want to find A bar, the closure, I have to look at the limit points, and you will see that 1 is going to be a limit point. So A bar is going to be the closed interval 0, 1. Now this is clear from the early example. Now the next example will take the same set and we'll change the topology. So we'll take with finite complement topology. We know the finite complement topology now. So this is T is the empty set union any subset of R such that U complement is finite. Now if I take the interior of A, you will see that the interior of A is going to be the empty set, as there won't be any non-empty open sets in A. I think it should be do, I think. Do not exist any open sets in A. And also I'm just jumping a little bit ahead because we'll show that the interior of a set is an open set and the closure is a closed set. So to understand this example, we might want to do the next definition. Okay, so we'll go to the next definition or the next theorem. So these are some properties of, and then we'll come back to this example. Okay, so for any subsets A and B of a topological space, so the first condition is interior of A is, I can write this a little bit different than the nodes. So first we will show that interior A is an open set. And then we can show that the interior A is the largest open set contained in A. Is the largest open set contained in A. And also we can show that interior A is the union of all open sets contained in A, and that's why it's going to be the largest. And third property is that A is open if and only if A is equal to interior of A. And the fourth one is if A is a subset of B, then interior of A is a subset of interior of B. And the fifth property is that the interior of A intersection B is the same as interior of A intersection interior of B.